All right, so this is what we have. Let's just look at this object and understand a little more about it. Okay, so one way to understand it is to realize that we could also write that as follows: sum over a and b of a vector C A E, right? Transpose, right? KAB, a 3 by 3 tensor, DBE. Okay, and for each of them, what I have here is the following: CAE and DBE, both of which we've encountered before, and we've also had occasion to note that they belong to R3. Okay, whereas this quantity KAB, right, it is a matrix, right, and it belongs to GL3, right? It is a general tensor. It does not necessarily have to be symmetric. In some special cases, it's symmetric. Okay. If you go through the process, you will discover later that it is symmetric for A equals B. Okay. All right. But for now, it's a general tensor in 3 dimensions. All right, so hopefully this helps. What I've done here is get rid of the implied summation over the indices that run over spatial dimensions and replace those with vector tensor products. Okay, now so each member of the sum is indexed by A and B. Okay, fine. So this is what we have here. Let's go through and fairly quickly compute the one of the other integrals, right? So next, consider the following: integral over omega e WH I Fi dV. Okay, this is the one we want to integrate now. So we have integral over omega e sum over a NA, no gradient on it, C A I E. That sum gives us our weighting function components, right? This times Fi, right? Or this actually multiplying Fi, and there's a sum implied over the I, dV. Using our usual tricks, and here I will take the liberty of skipping several steps at once, right? And still hope to get it right. Okay, so we get sum over A C A I E integral over omega C NA Fi determinant of JC d weak C. All right, and of course now we know that d weak C is dxc1, dxc2, dxc3. The integral over omega c is just a triple integral minus 1 to 1 over the 3 coordinate dimensions, right, in the bi-unit domain. Right. Okay. As before, we are going to call this integral here. We are going to denote it as f internal. All right. Note that it has an index a coming from the fact that it was computed with the basis function corresponding to node A, and it is each f internal A is a 3 vector, right? And this also we could write as sum over A, using the notation we use to write out our left hand side term. We have C A E transpose F internal A. Okay. All right. At this point, we've assembled the two somewhat easier integrals. We will return in the next segment to finish up the integral involving the traction terms.